Okay, so this is the second lecture on astrophysics and data analysis. What we're going to be covering in this lecture is gravitational wave sources, and then the lecture this afternoon I'll talk about data analysis techniques. So the plan for this morning's lecture is to go through a number of different types of gravitational wave source. For each one of those sources, I'll say a little bit about the astrophysics of the source, how these systems form, and our current understanding for how many of these sorts of events we're likely to see with LIGO and LISA. I'll say very briefly something about detection. I won't go into any detail, that's this afternoon's lecture, but I will say which detectors the source is for, where relevant, what we've seen with LIGO already, or what upper limits we have from LIGO already, and what types of waveform modeling we need to use in order to model the systems. And then I'll also have a couple of slides in each case about some of the science you might be able to do with observations of these systems. Okay, so the biggest category of gravitational wave source are compact binary coalescences. So the first half of the lecture will be entirely on these. So compact binary coalescence is a merger, so it's one of these n-spiral sources we were talking about yesterday, where you have two black holes or two neutron stars that are in a binary and they in-spiral under the gravitational wave emission and eventually merge. Now if we want to have a compact binary that coalesces, so it actually reaches the innermost stable orbit and then the two objects merge, the objects have to be very small, because otherwise they can't get close enough together to reach the ISCO. And so coalescences that we see with LIGO or LISA, you need there to be black holes or neutron stars in the system. White dwarfs are too big, and they can't get close enough. Okay. So how do you form black holes and neutron stars? That's what I'll be talking about first. And then I will say a bit about the different categories of comparable mass, well, different categories of compact binary we might have. Okay, so there are basically we divide compact binaries into three classes. This is partly an astrophysical classification, it's partly a modeling classification. I'll start off by talking about comparable mass binaries. So these are systems in which the two objects are quite similar in terms of their mass. So these are sources for LIGO when the two objects are formed from stars, so they have mass that's comparable to the mass of the Sun or a few tens of the mass of the Sun. And there'll also be sources for LISA, but then the black holes are much bigger, more like 1 million times the mass of the Sun. But the key thing is that when the two objects have similar mass, they we'll call them comparable mass binaries, and from a modeling perspective, you're then looking at using numerical relativity or post-Newtonian theory in order to model the waveforms. At the other end, we have extreme mass ratio in-spirals. This is when you have a stellar origin black hole falling into a supermassive black hole, and then one object is at least 10,000 times the mass of the other, and typically 100 or even 1 million times the mass, 100,000 or 1 million times the mass of the other. So these are the systems that you model in black hole perturbation theory that Eric's been talking about in the last few days, and their source is only for LISA because you need one black hole to be that many times more massive than the other, and so you need a million ton mass black hole. And then somewhere between these two are things we call intermediate mass ratio in-spirals. These are things that are neither comparable mass nor extreme mass. Now the boundaries are very fuzzy, but typically an intermediate mass system will have a black hole in it with mass 100 or 1,000 times the mass of the Sun. Now if such an object merges with something that is much lighter, so you have a 100 solar mass black hole merging with a neutron star, then that's a LIGO source in this category. If you have such an object merging with a much more massive black hole, then it's a LISA source. So a 1 million solar mass black hole with a 1,000 solar mass black hole is also an intermediate mass ratio in-spiral, but you'd see it in LISA rather than LIGO. We categorize these differently from the others. I mean, it's really a continuum in terms of mass ratio, but there are challenges in modeling in this middle regime, and astrophysically, the formation of 1,000 solar mass black holes is one concern. And so it is likely they form from a different process than the black holes in either of the other two categories. and so that's another reason for treating those as a separate source class. Okay, so how do we form black holes from and neutron stars from stars? I'm going to say a few words about stellar evolution. Some of this will be familiar to many of you, some of it might not be, but it just gives a basic overview. So the systems that we see with LIGO, these are so the comparable mass binaries LIGO observes. Typically, the black holes have mass. We've seen things as heavy as 35 times the mass of the Sun, but they're between a few and a few tens of the mass of the Sun. All of these black holes, we think, will form from stars. And the process is that the star goes through its normal main sequence evolution and then eventually collapses and creates a black hole. Okay? So for most of the life of the star, it's not a black hole, it's burning, and that nuclear burning process produces pressure, which stops the star collapsing. So there are a number of different nuclear processes that go on in stars. Which one is dominant depends on the mass of the star. We have something called the PP chain, which is burning of hydrogen to produce ultimately helium-4, and the CNO cycle, which involves carbon and nitrogen and oxygen, but it's also a hydrogen burning process because the carbon basically interacts with hydrogen, produces nitrogen, which then decays against carbon, interacts with some more hydrogen, produces nitrogen, oxygen, and so on. And this process goes round and round. It's what we call the CNO cycle. And the effect is it converts hydrogen to helium and releases nuclear energy. Okay? So this process goes on for billions of years in low mass stars, hundreds of millions of years in high mass stars. But eventually you run out of hydrogen, and then there isn't enough pressure support, so the star collapses a bit. But that means it gets hotter, and so it can burn heavier elements in a similar sort of process. So you initially burn hydrogen to helium, then you start burning helium to produce carbon, and you so on and so forth. So you gradually produce heavier and heavier elements from these nuclear fusion processes until you get iron and nickel, which are the most stable nuclear isotopes. Then it's not energetically favourable to burn iron to produce heavier things, and so this process stops. And then the star reaches the end of its life. So you'll hear people talk about the onion model of a star. If your star is heavy enough that all of these processes take place, you end up with a structure that looks a bit like this. You'll have an iron and nickel core in the middle, which is not doing any nuclear burning, it's just cooling. Outside that, there are slightly lighter elements which are burning to produce more iron and nickel, then falls inwards. Further out, you have lighter elements still, which are also undergoing nuclear processes and producing heavier elements that then sink towards the center. So you have this sequence of shells that are burning lighter and lighter elements as you go out. But in the center, this core stops at some point producing energy through fusion, and then it starts to cool, and as more stuff rains on it, at some point it can get too heavy to self-support. And you get a collapse, and that leads to a supernova and the formation of a black hole. Okay, so exactly what happens at the end of the process depends on the mass of the progenitor star. If you have light stars, they form white dwarfs, so they never get dense enough to be burning heavier elements. And so basically what happens when you run out of, our sun, when it runs out of hydrogen, it will never get hot enough to burn helium, and you'll just end up with a degenerate star made of helium, which will be a helium white dwarf, and that will then, which is supported by electron degeneracy pressure, and that will then just sit and cool and do nothing else more interesting. Slightly heavier stars form carbon-oxygen white dwarfs, so these get hot enough to burn helium, but not hot enough to burn carbon, and so again they then end up with this supported by electron degeneracy pressure, and then cool over the rest of the universe. Now there is a maximum mass you can have for a white dwarf. If you you've done statistical physics courses, you might have come across this Chandrasekhar limit. There is basically a maximum mass that can be supported by electron degeneracy pressure, and it's about 1.4 solar masses. So if your white dwarf ends up heavier than that, it will collapse and form a neutron star. And so similarly, if the parent star is too heavy, then this essentially the white dwarf core gets too big and collapses to form a neutron star. So these stars that just lead to white dwarfs don't explode. The ones that form neutron stars typically do. There are different types of supernova. Type 2 supernovae are associated with this core collapse to produce a neutron star. Okay, now neutron stars are also supported by degeneracy pressure. It's now neutron degeneracy pressure rather than electron degeneracy pressure. These are much smaller than white dwarfs. They're typically 10 kilometers across as opposed to 10,000, which is the normal size of a white dwarf with the mass of the Sun. Okay. Now, again, neutron stars can't get arbitrarily big. There's some uncertainty about what the upper limit on the mass of a neutron star is. It depends on that equation of state that Eric was talking about yesterday. But for masses, I think the largest one that's been observed is about 2.8 solar masses. Whether that is the upper limit or whether it's a bit higher isn't quite clear, but it's certainly true that you can't get neutron stars that are much more than 3 solar masses. And so, again, if the star is then heavier than, in this case, about 25 solar masses, you start to form black holes. This picture gets slightly more complicated as you go to even heavier masses, because at some point you get... Sorry, that number may be slightly inaccurate. I thought it was as high as 2.8. Maybe it's 2.6.
I think some people consider it an outlier, don't they? Like in a state.
Yes, but I mean, if it is a neutron star and it is that massive, then clearly neutron stars can be that massive. But yeah, that is very exceptional. So. So this picture, light stars from white dwarfs, heavier stars from neutron stars, heavier stars still for black holes, is nice and pretty, but at some point there's something else happens. If the star gets even more massive, then it can completely disrupt during the collapse process, and so you then end up with no black hole formed at the end. So there's this process called pair instability, which happens when there are heavier elements than hydrogen and helium in the star, and this process basically leads to very strong winds that push material off the star, so as it collapses it actually evaporates, and so you don't form any remnant at all. So it is expected that will be a spectrum of black hole masses with a gap. So the lightest black holes that you'll form will be a few solar masses. Exactly what that low limit is not clear. At some point you'll stop being able to form black holes until stars get really, really massive. Such things exist. So we expect that between about 40 solar masses and about 100 solar masses, though those limits are uncertain, we wouldn't be able to form any black holes at all. Okay? And there is weak evidence in what I have seen so far that there is this cutoff, because we haven't seen anything that is above 35 solar masses. And we are so we expect there to be many fewer of them than there are lighter black holes, but we can also see them much further away, and those two effects almost exactly cancel out. So we're almost uniformly sensitive to black holes of all mass between 10 and 100. We haven't seen anything above 40, so that's some weak evidence that there might be no black holes there.
Is there conclusive? Is it conclusive that the black holes that we've seen were formed as field binaries, as opposed to themselves being product or being second generation black holes?
That's a good question. The answer is no. I mean, there's nothing. So they're consistent with being field binaries. that is not to say they're inconsistent with having been formed by captures. What we can measure for them is their masses. You can form black holes like the ones we've seen through both processes. So at this point we can't say. I think, yes, so the answer to your question is we can't tell the difference yet. Once we have 100 events, then maybe we start to see some indication. Okay, so that's the process for isolated stars. Your stars collapse, they form black holes or neutron stars. That's fine, but we don't care about individual neutron stars or black holes unless those black holes then find other black holes and form binaries that way. What we care about are forming binaries. Okay? So what you need then is two objects that are in a binary, both forming compact remnants. Okay? Now, having objects in binaries is easy. 70% of stars are in binaries, so that's not a problem. But there are a number of constraints on the systems if you're going to end up with a binary at the end that is bound and can therefore merge under gravitational wave emission within a Hubble time. So the typical schematic of how you might do this, you have the two stars, the more massive one forms, undergoes a supernova and forms a neutron star first. The secondary then continues its evolution. At some point, the objects get close enough that this star overflows what's called its Roche load. So that basically means it gets too big for the gravitational potential in the co-rotating frame, and material falls off the star onto the other one. This process leads to what's called a common envelope, in which you have two cores, the first remnant from the heavier object and the core of the secondary star, both orbiting within the envelope that was the envelope of the secondary. Now this process, it's called it's called common envelope evolution. This is important if you're going to get a binary that LIGO could observe, but it's very, very poorly understood. Essentially, the argument is that once these two cores are in this envelope, you get frictional effects with this surrounding material, which drives the binary to much closer separations than it starts with. And so this can then give you a fairly tight binary, so that by the time the second core undergoes a supernova, the two objects are close enough that that supernova kick doesn't disrupt the binary, and they end up still close enough to each other that they then merge through gravitational wave emission within a Hubble time. Now this common envelope evolution, you'll see books that talk about it. They typically characterize the whole process by a single number, which is an efficiency, which is basically the fraction of the binding energy of the binary that is dissipated during this phase. That's a number of order unity. Whether it's 0.01 or 1 is very uncertain, and it's one of the things that perhaps understanding the LIGO systems will start to shed some light on. Once we know how many of these things are being formed, then we can start to say something about the efficiency of that process. Okay, so prior to LIGO's observations, we had good observational evidence for all of these types of compact remnant. White dwarfs, we see lots of them. You can identify isolated white dwarfs from their spectral characteristics in light. And we also have these things called cataclysmic variables, which are white dwarfs that are accreting from companions, and these are stars that appear to pulsate regularly. We have evidence for neutron stars from pulsars. We see pulsars, these radio sources that are periodic, and they are believed to be produced by rotating neutron stars with jets of material coming off them. And we know many of these, and some of these pulsars are in binaries, and so that tells us also that there are compact object binaries which can merge within the edge of the universe. So prior to LIGO's detection, it was the observation of the 4 neutron star binaries that gave us all of the information about how many black hole binaries and neutron star binaries LIGO might see. But this was based on an extreme amount of extrapolation. I'll show you in a couple of slides. the predictions for rates prior to LIGO's detections, what we believe now, and you'll see how that they've tightened up by 2 orders of magnitude just from having 6 events. We also see things called X-ray binaries, and these are believed to contain black holes. You see sources that have X-ray emission. It's a binary system, and it's believed that X-ray emission is because you have a main sequence companion to a normal star that is so material from which is accreting onto a companion that is a black hole. If it's a black hole, then the material gets very hot, and you produce X-rays, and you see these things in a number of systems in the UK. In the Milky Way. Okay, so this slide's a bit old. This was a summary of all the black holes and neutron stars, well, a subset of black holes and neutron stars that were known a few years ago. See that all of the black hole candidates, the masses that were estimated were rather uncertain. It's because it's very hard to infer the mass just from looking at the X-ray emission. But then LIGO came along, and we now have seen 6 separate black hole mergers, and also 1 neutron star merger. So these are all the events that have been published so far. There are a few more candidates that are currently still being analysed, so this number may grow a bit in the near future, and LIGO will start its 3rd observing run in February of next year, and then we should have some. Okay, so these sources that are at the start are sources for LIGO. If you have 2 objects with mass similar to the Sun, then the gravitational wave emission is in the few hertz to a kilohertz band. The way you dig them out of the data is using match filtering primarily. I'll say more about that this afternoon. You can also detect these sources using unmodelled techniques. So these are what we historically called burst searches. I'll also say a bit about that this afternoon. To model the gravitational wave emission from these systems, you use a combination of post-Newtonian theory and numerical relativity. Post-Newtonian as well for the in-spiral phase, before the objects get too close, and then at some point you need numerical relativity to take the system through that final phase of in-spiral phase. And as you heard about in the first lectures this week, you can combine these post-Newtonian results and numerical relativity results in phenomenological models, which are what we actually use when we're trying to dig these sources out of data. So there are a couple of families of these. There's the EOV model, which Alessandra was talking about. There's also something called IMR phenom, which is less physically motivated than EOV. It's more of a phenomenological fitting formalism. Okay, so I'll finish off this section by saying a bit about what LIGO has told us from the observations of these systems we've made so far. One of the primary scientific results from these observations is knowing how many of the events exist. Okay? Well, that sounds a bit silly, but as I was saying earlier, to predict the number of black hole binaries previously, what we'd done was look at the number of neutron star binaries that existed and say, well, if there are this many neutron star binaries, there must be this many black holes, and hence there must be this many black hole binaries. So it's a very indirect process. But now that LIGO started to see these events, we can count how many events we see, and we know how sensitive our detector is, so we can work out how far away we could have seen these events, and so that can translate those numbers of detections into a merger rate per unit volume per unit time. This plot is from, this is relatively old, this number is the most recent number. Our current estimate is that there are between 12 and 213 mergers of black hole binaries in every cubic parsec in the universe every year. Okay, so that means there's about 1 merger in every galaxy every 50,000 to 1 million years. Okay, so this tells us we're going to see one in our galaxy, but this number is sufficiently high that LIGO is going to see lots of these events. Okay, we've seen 6 so far, with accumulated observing time of about a year, and the detectors are only going to get more sensitive. Okay, so these are the predictions looking forward about the numbers of events LIGO is going to see. there are different scenarios here. So this 2015-16, 2016-17, these are the 2 observing runs LIGO has done so far. So you'll notice there is, sorry, this is for neutron star binaries. I forgot to put in the table for black hole binaries, apologies about that. So there are numbers here which say how many events we actually saw. For black holes it was 3 here and 3 here so far. These other columns are predictions for the future. So 2018-19, which is actually now going to be 2019-2020. This is the 3rd LIGO observing run, which is scheduled now to start in February of next year. The prediction there is that we will see about 5 times as many events as we saw in the most recent observing run. Okay, so for neutron stars, we saw 1 in the last observing run. We expect to see 5 in the next observing run, but the range is 1 to 50. Okay? Similarly for black holes, we saw 3 in the last observing run, plus a couple of candidates, so we're going to expect to see order 15 to 20 in the next observing run. Okay? 2020 plus, this is when advanced LIGO reaches design sensitivity, so this is in 2 or 3 years' time, and then we have another factor of 5 or so improvement in rate. So we're talking now about as many as 25 neutron star events a year, and potentially as many as 100 black hole events per year. Then you get into 2024 plus, this is the point at which the extra LIGO detector that they're building in India will have come online, and perhaps also Kagra, the Japanese detector, and then that gives you another factor of a couple. So we'll get to the point in the next decade that we would be expecting to have tens of binary neutron stars and hundreds of binary black holes per year. Whether we can actually handle analysing all of that is another question, but yeah, it sounds great. Okay, so this is the prediction that was made before we had our very first event, and it just shows you the uncertainty that existed before LIGO started making measurements. This was the range of plausible rates that could be for neutron star binaries and black hole binaries. You notice that for neutron star binaries, the rate was between 0.01 in some suitable units to 50, so that's almost 4 orders of magnitude, and it's the same for binary black holes. It was 10 to the minus 4 to about 1 in these units. So we have 4 orders of magnitude uncertainty in rates, and that's come down to this number 12 to 213, which is a factor of 1 order of magnitude uncertainty. And that's just based on 6 observations. Okay, so some other results from LIGO. It was a bit of a surprise that the black holes were as massive as they were because of the existence of this mass gap that I told you about. What's shown on this plot is the predictions of a number of different simulations of different metallicities. So to an astronomer, a metal is anything that is heavier than helium. If stars have those heavier elements in them, they tend to have stronger winds, and so you lose more mass from the star, and that stops you forming these very heavy black holes. So going from the top to the bottom, the metallicity is increasing, and each curve indicates the mass of a black hole that would be formed as a function of the mass of the progenitor. Okay? And you'll notice that, except at the very low metallicities that you only have in the very early universe, all of these curves tend to turn over and get flat at around 40 solar masses. Okay? So this is saying that for these sorts of metallicities, you can't really create black holes that are heavier than 35 to 40, which was the mass of the first black hole that we saw. So it was a bit of a surprise. It's not inconsistent with this, but the fact that it was right at the edge of what was thought to be plausible was a bit of a surprise. One argument for why this might be is that some of the stars that might undergo this pulsational pair instability, when you get massive enough that becomes an issue, what it might do is just dissipate some mass from the star and then reduce it to the lighter stars, if you see what I mean, which then evolve and form black holes as normal. And so essentially all of these stars that are too heavy to form black holes actually end up as slightly lighter black holes, which then form things of around 40. And so you get a pile up of black holes at this edge of the pair instability gap. Okay, so that's one plausible model that would explain why the first event we saw happened to be so massive, though we need more events to be sure. LIGO's also placed some constraints in GR, and GR is still correct, I'm pleased to know. So this is one example that was from the first event. How these sorts of constraints are done is that corrections are added into the phasing of the gravitational waves at different post-Newtonian orders. So we have a prediction from GR about what the phase of the gravitational wave should be as a function of time. You can add a correction to that, and then you can take your data and say, is there any evidence that that correction is present? And if not, can we place a band on the size of that correction? These yellow squares are the bands that were placed from 1509 and 14, and the blue triangles indicate bands that have been placed from observations of binary pulsars prior to that. Okay, so with the exception of the 0 PN correction, which is a very weak field, and so we're not really probing that in observing 1509-14, we beat the pulsar bands everywhere with this first event, and similar constraints have been placed on using subsequent systems. The binary neutron star event was also quite exciting for these sorts of things because we saw a counterpart to it, and the delay between the counterpart arriving at the Earth and the gravitational waves was 1.7 seconds. Okay? And so that places a constraint on the speed of light. It's not a completely model-independent constraint. Sorry, not the speed of light, on the speed of gravitational waves. It's not a completely model-free constraint because you have to say something about when the EM radiation was emitted relative to when the gravitational waves were emitted. But if you assume, which is the case for all models, that the gravitational waves come before the gamma ray burst, which was what we're seeing, then this 1.7 second delay places a limit on how different the speed of light can be from the speed of gravity. And this had quite a big impact in certain areas, in particular cosmology. There were a number of things called beyond Horndeski theories that were used to explain the accelerating expansion of the universe. These all have speeds of gravity that are different to the speeds of light, and so these are all ruled out by this one observation. Another thing this neutron star event enabled us to do was measure the expansion rate of the universe using gravitational waves. So the idea here is that what you can measure very well from a gravitational wave event is the luminosity distance to the source. And that is, you don't have to calibrate this to any local distance scale, it just comes directly from measuring the strain. So we can get a very accurate estimate of the luminosity distance to the source. That allows you to constrain the rate of expansion of the universe, but only if you know the recession velocity, so you know the redshift of the source. You cannot get that directly from the gravitational waves, but if you have a neutron star event with a counterpart, which we did, then that counterpart tells you the host galaxy, and so you know the redshift. So you therefore know how fast the source is moving away from you and how far away it is, and so you can work out the ratio of those two, which is the Hubble constant. That's the local expansion rate of the universe. Okay, and this is the measurement we got, 70 plus 12 minus 8. Now this is much less precise than existing measurements. This narrow green band here is the estimate of the Hubble constant that comes from the Planck satellite. This orangey band is the estimate that comes from using type 1a supernovae. We're consistent with both of them, but much more uncertain. But this is the first time we've done this measurement. The first measurement of the Hubble constant by Hubble, he got a value of 500. So we are doing much better than that, but technology has improved in the century since he did that. So this number is going to get better as like the square root of number of events as we see more neutron stars. And so the hope is in about 10 years, if we're seeing as many events as we expect, we should get down to a 1% level on this measurement that will allow us to say which of these two, which are inconsistent with one another, is right. So another thing that made a lot of press from this neutron star event was the production of gold. So it was hypothesized prior to 1708-17 that following the merger of two neutron stars, you would have something called the R process taking place in the material that was ejected. So the R process, it's a nuclear fusion process, but it's one that can create elements heavier than iron and nickel. Okay? Now that's energetically unfavorable, but it's possible if you have very hot material, so there's lots of energy available, and also very neutron-rich material. So you tend to get neutron capture onto elements. Those neutrons then, so those are unstable, the neutrons decay, but leave a proton in the nucleus, and so you can generate heavier atoms through this process. Okay? So this R process was hypothesized to take place following a neutron star merger. Neutron stars are made of neutrons, and so that is very neutron-rich material. When you bash them together, you get a very energetic, hot, neutron-rich plasma, which can then undergo this R process and produce heavy elements like gold and platinum. Now, interestingly, from seeing one of these events, it is consistent with all of these heavy elements being made in neutron star mergers. Okay, so this panel on the left-hand side here, this is the blue region horizontally. This is the range of possible ejector masses. So this is the range of possible masses and solar masses of material that's flung off in the neutron star merger. This vertical black band, this is the inferred rate of neutron star mergers from the fact that we've seen one having observed for a year at the sensitivity we have. And so then the product of this ejector mass with the rate is the rate of production of these R process elements. And this red band is the constraint from observations of the amount of gold and platinum in the universe. Okay? So the fact that this red band passes exactly through this region bounded by the blue and black curves is telling us that this process can produce all of this R process material, which was, as I said, believed but not known prior to that first event.
What was the plot on the right?
That is a good question.
You don't have to answer.
So I think this is just so this is basically where the blue region comes from. It depends a bit on we can't infer directly the ejected mass. That's based partly on modelling, and the predictions depend on the equation of state of the neutron star. But these four curves here are different equations of state, and they're basically all producing about the same amount of ejected material. Okay, so that's all kind of so I think I have a couple more results from LIGO, and I'll move on to LISA, compact binary sources. One other thing that LIGO has tried to do, and not yet seen, is look for these intermediate mass black holes. So as I said earlier on, the reason we distinguish intermediate mass inspirals from other types of inspiral is because we don't know much about whether intermediate mass black holes exist. Okay? Now, one of the processes by which these can form is runaway collisions in globular clusters. So globular cluster is a dense bound system of stars. We see these. There are plenty of globular clusters in our own galaxy, and they're also observed in other galaxies. In these globular clusters, the stellar environment is a bit denser, and so you can imagine that a process called runaway collisions can take place. The stars form black holes. Those black holes tend to be heavy, and they sink to the center of the cluster, and when they encounter other black holes, and these can merge and grow black holes more quickly, and hence you can end up with black holes of about 100 or 1,000 solar masses in the centers of these globular clusters. Okay, so if these intermediate mass black holes exist, it's very controversial about whether they do or not. There is some observational evidence, but it is not widely, there's no wide consensus about whether these objects that may be intermediate black holes really are. that we have observed in the census probability clusters some ultra-luminous X-ray sources, and one of the models for that is that it is, in the same way that an X-ray binary is a black hole that's accreting from a companion. It's believed these ULXs, ultra-luminous X-ray sources, might be intermediate mass black holes accreting from surrounding dust or from companions. And so we have seen ULXs in the census probability clusters. These may be intermediate mass black holes, but it's very uncertain. But it's sufficient motivation for LIGO to try and place constraints on the numbers of intermediate mass black holes that might exist. This is the most recent result from LIGO. The plot here is the mass of one component and the mass of the other component, and each dot on this panel is a constraint on the rate. Okay, so we're saying that we know that the rate of where is it? Let's see the scale. I think it's about 300 plus 300 solar mass in spirals is less than 20. The rate of 100 plus 100 is less than 0.93 per cubic gigaparsec per year. Okay, now we don't have anything to compare these against. We can't say, well, we expect the rates to be at least 1 per cubic gigaparsec per year, and so we expect to see these soon. At the moment, since we don't know if these things exist or not, all that LIGO is trying to do is place limits, which then can inform models. Okay, so summary of some of the science you can do with comparable mass LIGO compact binaries. We talked a bit about the astrophysics. We're starting to probe things like mass distributions, spin distributions of black holes and neutron stars. This will tell us about their formation processes, and in particular, we hope one day to learn something about that common envelope evolution phase, which is very uncertain. I'll show a slide after this about neutron star equation of state. So as Eric was talking about yesterday, the neutron stars get tidally deformed when they're in tight binaries, and that leads to a correction to the gravitational wave phasing that in principle you can measure. If you can measure that deformability, it tells you about the relative compactness of the equation of state, and hence you can start to learn something about neutron star structure by measuring these tidal effects. And we can also do tests of general relativity, as I showed already, by comparing predictions of GR to observations. For that neutron star equation of state constraint, this paper was on the archive a couple of weeks ago. So I had a discussion with Eric earlier about whether the thing that LIGO is measuring, which is tidal deformability, is the same as the Love number that he was talking about yesterday. It seems that that is not obvious, but it is sometimes assumed to be the case. But what LIGO can measure essentially is a correction to the phasing of the gravitational waves that it comes about from the tidal deformation of the neutron star. So the neutron star gets deformed, that tide lags behind the orbit and leads to an acceleration that changes the evolution of the binary. Okay. That comes in at 5pn. We don't have 5pn corrections in GR, so there is people argue that the correction from the tides is big and the other corrections might be small, but that's not fully known, so there are certainly uncertainties here. But if you assume that all of that 5pn effect is coming from tides, you can place a constraint on this deformability parameter. And this is what you get. So we have a posterior. So lambda 1 is the tidal deformability of one of the neutron stars, lambda 2 is the other. The posterior is peaked away from 0, but it is consistent with at least one of them being 0.
In the analysis, the original paper that was published, weren't the two tidal deformabilities of the neutron stars treated as not being the same or not constructed the same material? So
right. So in the original detection paper published last October, there was a constraint, there was a plot that looked a bit like this, that was just trying to measure the tidal deformabilities entirely independently. This more recent paper has done a slightly different analysis in which it assumes that the equation of states of the two neutron stars are the same, and that gives you a slightly tighter constraint because that gives you extra information which helps break degeneracies. Okay, so these results are assuming a common equation of state. That's what these lines going from the top left to the bottom right indicate. And again, assuming a particular equation of state and these sorts of results, you can get a distribution on the radius of the neutron star. As we said, neutron stars are about 10. That still seems to be the case. We can say reasonably confidently that the neutron star radius in this particular case was less than 14, most likely less than 13, but again, those constraints will become stronger as we get more events. Okay, so I'm going to move on to LISA, compact binaries, and there are a number of different types of these, starting with the LIGO sources. Okay, so 150914, this first LIGO event would actually have been observable by LISA, if LISA was in existence at the time of that event. Okay, now this is because, so these sources weren't talked about for LISA previously, but that's because we assumed that black holes, the LIGO would see, would tend to be lighter. As I said, it was a bit of a surprise that the first events were so massive. We were expecting them to be more like 10 or a few, 10 or 20. The fact that they're 30 and 35 makes it more interesting because it means that they're brighter in the LISA band than you might ordinarily have expected. Okay. So you'd only just have seen 150914, whereas this was a very clear event in LIGO, even though LIGO was it's not reached its full design sensitivity. It would be marginal in LISA. You'd get a signal-to-noise ratio of about 8 to 10, which is the threshold for detection, if you observe for the entire duration of the LISA mission of 5 years. Okay. So the thing that's nice, we expect to see more of these when LISA is flying, and assuming LIGO is operating at the same time or something else on the ground, then you can do better science by combining these observations. So LISA provides better sky location accuracy than LIGO. That's because LISA observes the source for years, and so LISA moves around the sun, and you can get to triangulation from the fact that you're effectively taking observations separated by the radius of the Earth's orbit. For LIGO, you don't get very good sky location from a single detector because you're only getting a burst and you don't know which direction it's coming from. In fact, we have more than one detector does improve that sky localization, but we will do better if we have both LISA and LIGO than we can do with LIGO alone. Now, the number of events is rather uncertain. It depends critically on these heavy things. So there was a paper shortly after the 150914 announcement by Alberto Susanna, which made some predictions and was talking about tens to hundreds of events being seen by LISA. I think that's probably an overestimate, and that's because it was assuming the black hole mass function extended up to 100 solar masses. So it was a model in which there wasn't this mass gap. And as I said earlier, there is some evidence already from LIGO that that mass gap is there. And you really can't see things that are much lighter than 150914 with LISA. So the number of these events is critically important to having LISA binaries. But if this process where slightly heavier stars also form 30 solar mass black holes does take place, then maybe we have more of these sorts of events, and so you'll see lots of these things when LISA flies. There are, of course, other types of LISA source. These are the more traditional things that people talk about for LISA, and these typically have much more massive black holes in the center. Okay? So as we were talking about yesterday, the frequency of gravitational waves scales with the mass of the system. The bigger the mass, the wider the binary, so the lower the frequency. So F scales like 1 over m. LISA is going to be operating in the millihertz band. LIGO operates with peak sensitivity around 100 hertz. So you've got a factor of 10 to the 5 difference in frequency, and so you want a factor of 10 to the 5 difference in mass. So whereas LIGO is looking at 10 solar mass systems, LISA is looking at 1 million solar mass systems. So the range of masses for LISA is roughly 10 to the 5 to 10 to the 7. These black holes are seen to exist in the centres of most galaxies. We see things like AGN, active galactic nuclei, where you get this strong point-like emission from the centres of very distant galaxies, and that's believed to be accretion of material onto these massive black holes. Now 10 to the 5 to 10 to the 7 is quite low mass for the sorts of things you see as AGNs. These tend to have masses 10 to the 8, 10 to the 9, which are out of the LISA range. But those bigger black holes have to fall from lighter black holes, which is why we believe these sorts of things exist. Okay, so where does this observational evidence come from? Some of it is direct, some of it is indirect. There are a number of, so you'll hear people talk about the M sigma relation and the L sigma relation and various other things. These are observational correlations between properties of galaxies and other properties of galaxies. So in particular, there appears to be a correlation between the mass of the black hole in the centre of a galaxy and the total mass of the galaxy. And there's also a tight correlation between the velocity dispersion in the centre of the galaxy and the total galaxy mass. And that velocity dispersion in the centre is also closely correlated with the black hole mass. So the sigma they talk about in these sorts of relations is that central velocity dispersion. It's the typical velocities of stars orbiting in the middle of a galaxy. And then the M can either refer to the black hole mass or to the total mass of the galaxy, which is defined as something called the bulge mass. For a spheroidal galaxy, it's essentially the total mass, but for a spiral galaxy, it's just the mass of the spherical bit in the middle and not the disk. Okay, so there's lots of observational evidence for this correlation. These are a bunch of observations. This plot's a couple of years old now. But what you'll notice is that the masses of the black holes here are mostly above 10 to the 7. And yet the LISA band is below 10 to the 7, it's 10 to the 5 to 10 to the 7, and we don't have very many observations down here. Okay. But that's good, because when LISA observes these things, then we will learn about that, provided that they are there. Okay. Because we can't observe those lighter systems, we don't know exactly how many there are, but we can make educated guesses because the process by which the heavier black holes form is believed to be by mergers and accretion onto those lighter black holes. So the fact that we see a certain number of heavy black holes tells us that there must be lots of lighter black holes. Okay, so how do they become LISA sources? Well, you have black holes sitting in the centres of galaxies, in fact in the vast majority of galaxies, and we observe that galaxies merge with one another. So these are all images taken with the Hubble Space Telescope that show either pairs of galaxies or groups of galaxies undergoing mergers. So we know these mergers take place. Galaxies are moving around and they can encounter one another and undergo gravitationally driven mergers. And so if there are black holes in the centre and their host galaxies merge, you expect eventually those black holes to merge, because the black holes are the heaviest objects in the post-merger galaxy. Heavy things tend to sink to the centre of gravitational potentials, and so these black holes eventually end up in the middle, where they encounter one another, they form a binary, and then they merge. Now, this is the most likely outcome. The most likely that we will end up with these two black holes merging, but there are a number of issues in this whole process. The physics is a bit uncertain. You may hear people talk about the lattice parsec problem. It's very easy to get the black holes to within 1 parsec of one another. This happens by encounters with stars that take away energy from the binary, but at some point you run out of stars, and so getting the black holes closer than that 1 parsec is an issue. And at 1 parsec, it takes more than the age of the universe for the two black holes to merge. Okay, so that's a problem, but it's not believed to be so much of an issue now. When you do better simulations, including gas and so on in the centres, black holes get much closer fairly naturally. Another issue is kits. So when so with black holes, we know when black holes merge, they get a record kit that can unbound the black hole from the galaxy, so it can leave the centre, and then that galaxy doesn't have a black hole anymore, and so next time it merges, you won't get a binary. Okay, so there are some uncertainties here, but the general picture is you have galaxies that contain black holes, the galaxies merge, the black holes find one another, and eventually they merge and they emit gravitational waves that LISA can detect. Okay, now in the universe today, the average time between mergers of galaxies is about 25 gig years, so that's about twice the age of the universe. So the merger rate today is not very high, but the merger rate was higher in the past, when, at least partly because of expansion of the universe, but in the past, black holes would be smaller because they've grown over time. And so this is perfect for LISA. We have a higher rate and lighter black holes in the past, so that's the sources that we're looking for, but we need to be able to see them to very great distances. So people simulate this. They simulate this using things like merger trees. You start with a population of galaxies, well, typically dark matter halos. You put black holes in some subset of them, and then you just evolve the whole thing. When these halos merge with one another, the black holes may or may not merge. You can keep track of the masses of the black holes, and so you can simulate the population of black hole mergers. So again, Alberto Solana did a lot of this work with Monte Monterey and Francisco Hart back in the early 2000s. And you get different distributions of sources in terms of where they are in space and redshift, and what their masses are, depending on your assumptions in the model. Okay, so there are two, the top panels here and the bottom panels here are making different assumptions. The top and bottom panels here, the different panels here are different masses of black holes. This is the most relevant one for LISA. This is one particular model. But if you do different models, you end up with slightly different predictions. In particular, there is a big difference in what you get depending what you assume about the mass of the initial black holes. So we see black holes in the centers of most galaxies. We know if there are black holes there, then when those galaxies merge, the black holes merge, so the black holes get heavier. We also see that these AGN, we see black holes that are accreting everywhere in the universe, and so we expect black holes to also grow by absorbing material from their surroundings. But you have to start with black holes for these processes to take place. Now, there are two basic models that people use, which are called light seed or heavy seed models. So in the light seed model, you assume that there's an initial generation of stars that have mass that are very low metallicity and very big, and they can produce black holes with mass as much as 100 times the mass of the Sun. And this is only possible because the metallicity is very low. These are called population 3 seeds. You put population 3 seed black holes in the centers of most halos and then evolve things forward. This means you get a bunch of mergers that have quite low masses and occurring at high redshift. There's another model, the heavy seed model, assumes that black holes seeds are heavy, obviously, but the way that mechanism works is you assume that you have a very large collection of gas, so essentially a gas cloud that again has low metallicity, and so it can directly collapse to form a black hole that is much more massive, and you can get things as heavy as 10 to the 5 solar masses in that way. Okay? So depending whether you assume light seeds or heavy seeds, you get different predictions for what LISA will see, but the total numbers of events are not actually that different because you have to constrain both of these models to get the right number of heavier black holes that we do observe. Okay. Our final ingredient in understanding numbers of events that LISA can see is understanding where LISA can see them. And the answer is, for the right mass, basically anywhere. So these coloured contours here are labelled by signal to noise ratio. The outer one is 10, and 20, 50, 100, 200, 300, 500, 1,000. I think there's a 2,500 at the bottom there. Okay. So this is signal to noise ratio. As I said yesterday, we need, so this is a measure of how detectable something is if you're doing match filtering. We think we need SNR above 10, or above about 8 or 10 in order to pull an event out of the data. So everything inside the purple band is in principle detectable. So if the black hole has a mass 10 to the 5 solar masses, you can see it out to a redshift of 20, which is very early in the age of the universe. Okay. And it's this long reach that LISA has, which is what allows us to see lots of these events. So with our current, the LISA satellite hasn't been built yet. It's entered phase A, so the design is closer to being finalised. So there are lots of different designs that have appeared in the literature over the years. People talk about classic LISA, which had 5 million kilometre long arms. The current configuration has 2.5 million kilometre long arms. It doesn't make too much of a difference in terms of numbers of events, but it does make some difference. Our current baseline, so we would expect, so our current baseline would see about 350 events under these light seed models, and about 550 events under heavy seed models. This is over the duration of the mission, which was assumed in this case to be 4 years. Okay. Of these events, there would be 150 light events at very high redshift, so redshift greater than 7. Heavy seed model would also have quite a few events at redshift greater than 7, because we can see them wherever they are. You lose some of these events if your detector is only 1 million kilometres long, but you mostly lose events in the light model. That's because those are the things that have lower signal to noise ratio. If you went back to this 5 million kilometre configuration, you don't gain too much. Okay, so if LISA sees these events, we're going to want to measure parameters. I'll talk this afternoon about how the procedure for doing extracting parameters from signals. But the most relevant numbers for this bit of a talk are how well we'd expect to measure things. And these are kind of typical accuracies. This is not for the current baseline, but it doesn't make too much of a difference. We expect to measure the masses to at least 1% precision, hopefully 1/10% precision. We similarly expect to get percent level measurements of spin for both objects, and luminosity distance measurements of a few tens of percent. This is not particularly good. It's not very good for things like Hubble cluster measurements. It's a bit too big. But the reason it's fairly large is because a lot of the SNR comes out in the merger phase, and so you don't get this triangulation that I was talking about earlier for the LIGO binaries. So over 2 years, we would expect LISA to measure both redshifted masses, so both masses in the binary to 1% for about 100 systems. So there are 3 numbers here, 7 and 110. This last one is a sort of pessimistic model in which we assume that there's a long delay between a galaxy merger and the merger of the binary. And so it reduces the number of systems a lot, because many of the things that for which the galaxies have already merged don't merge, the binary doesn't merge before today. We expect to measure the spin, so the rotation rate of the heavier black hole to about 1% for a few tens of systems. We expect to get decent distance and sky localization, by which we mean 10 square degrees localization of the sky, and a distance precision better than 10% for about 10 or 20 systems. So this is in 2 years. The LISA mission requirement is that it lasts for 4 years, but it is going to have enough consumables to last for 10. So if it really does last the full 10 years, then we're talking about 50 odd events with very good sky and distance precisions. Okay, so a couple more things, then I think we'll take a break. As I've said, throughout these heavier binaries are sources for space-based interferometers. You detect them in the same sort of way that you detect the LIGO binaries using a combination of match filtering, possibly on model searches, and in LISA people have looked a lot at using stochastic searches. If you don't know what these things mean, that will be hopefully clearer after this afternoon's lecture. Modelling LISA binaries is exactly the same as modelling LIGO binaries. You have a combination of PN and numeric productivity. The one complication is that these events are going to be much higher signal-to-noise ratio. We don't realistically expect to see things in LIGO that have SNR much above 100, but you can get things with SNR as high as 1,000 for LISA. And so if you're measuring things with much louder, you can measure things much more precisely, and so you need a much more accurate waveform model in order to do that. So that is an open challenge, which maybe some of you in the room will work on over the course of your careers. Okay, so final couple of comments on these binaries. What sort of science will we get from these? So, as I emphasised when I was talking about the event rates, the astrophysics of these LISA binaries is also uncertain. So, in the same way that the LIGO astrophysics was so uncertain that we had 4 orders of magnitude uncertainty in rates prior to start making LIGO observations. This is also true for LISA. We don't know a huge amount about these black holes because they're the light ones that we can't see electromagnetically. And so once we start measuring the numbers of mergers, their redshift distribution, their mass distribution, and their spin distribution, then we can start to say something about the evolution of galaxies, and this will improve models of that. We can do tests of GR with LISA binaries in the same way as LIGO binaries. The tests are quite similar, but again, this high SNR makes things better because you can detect much smaller differences in the phase of your signal from your predictions of GR. But of course, that's only possible if you can do the GR simulation required. Cosmology, so if we get counterparts to some of these LISA events, we can do Hubble constant type measurements, again with these in the same sort of way that we've done for LIGO. One problem that you encounter in LISA that you don't encounter for LIGO is the effect of weak lensing. So gravitational waves get bent by matter in the same way that light does. So this is lensing. And it becomes more of a problem as you look at sources that are further and further away. And so, since these LISA binaries are mostly at redshifts of 1 or higher, we expect there to be weak lensing corrections to the distance estimate at the order of a few percent. And so that limits our ability to do cosmology because we can't unless we can somehow undo those weak lensing corrections. Another thing that LISA will tell us will be about size of kicks. So you get enough SNR in LISA that you can potentially directly measure the accumulation of the kick in the gravitational wave signal. Even if all you measure is the parameters of the system, from that we can predict the size of kicks. And so from this population model that we constrain by looking at these events, we can start to constrain the size of kicks, and that will tell us how many of these mergers lead to the ejection of black holes from galaxies. And that could have important consequences for the astrophysics of galaxies and their central black holes. Okay, so I'll finish with one example of some work that we looked at. So as I emphasized, there are these different predictions for the formation of black holes in the sense of galaxies. They predict very similar numbers of events with LISA, but the properties of those events are very different. And so what you can hope to do by using LISA observations is to tell the difference between these light seed models and the heavy seed models, and also attempt to tell the difference between models of accretion processes. Okay, so this is an example we looked at. This was for classic LISA, it was a few years ago. But we asked how well we could tell the difference between light and heavy seed models and between models that had something called efficient accretion versus something called chaotic accretion. Okay, the difference in those accretion processes, efficient accretion is when all of the material accretes in a single disk. So that means it coherently adds angular momentum and it spins the system up. Chaotic accretion, you have the same amount of material added, but it's over many small accretion episodes. So you get a sequence of accretion disks. These are not all in the same plane, and so you're stochastically adding angular momentum rather than doing it in a coherent way. Okay, so the main difference between the efficient and the chaotic accretion processes is you get much higher spins with efficient accretion than you do with chaotic accretion. And this analysis, we only looked at the masses. Okay? And so we'll see that and 1 in this table indicates we can tell the difference very well. So we have 1s when we're talking about an L, which is a L for large seeds. So L versus S, we tend to have 1s in this table. That means we can tell the difference between a heavy seed and a light seed model very easily. Where we have efficient and chaotic comparisons, then it's less clear. The numbers are a bit lower. Even just using the masses, we can tell the difference to some extent. When you fold in the spin information as well, then you do very well indeed.
One question.
Yeah.
How can you measure whether it is the Chi-P or Chi-F of the binary? Or it would be the same as LIGO?
Right. So it's going to be similar to LIGO. You do get more of the in-spiral, and you also get the higher SNR. So essentially, the reason that you can measure certain things better with LISA than LIGO is the fact that the SNR is up by a factor of 100. So that gives you 100 times better precision. Ultimately, what you're trying to measure, it's the same model, we've just scaled the frequency. And so the same degeneracies are present for LISA systems as are present for LIGO systems, but you have that benefit of higher SNR. There's also a chance for LISA that we see things that are a bit more extreme in terms of mass ratio, but are still comparable mass. We can get things of 1 to 10, 1 to 30. If you have that slightly more extreme mass ratio, you see you have more cycles in the strong field, where the precession from the spin is contributing to the waveform. And so that can also help. Okay, so this final plot. In practice, the universe is not going to be either of those simple models. We're not going to only have had light seeds or only heavy seeds. We'll have some combination of the two, and so what we did was just say, well, let's suppose we observe a mixture of these. Can we tell what fraction of black holes come from light versus heavy seeds? That's what's plotted here. We injected 45% light seeds, I think, and we can tell that's about what is there, although the uncertainty is reasonably big. Estimated 0.5 plus or minus 0.2, and this has to be a number between 0 and 1, so we've narrowed it down to maybe half the possible range. But at least we can say that there are both, rather than being confused about whether seeds were all light or all heavy. Okay, I think we'll take a coffee break now, and then when we come back, I'll talk about emeries